Hello, so remember in the last video we really got under the skin of parabolas and we really understood some of the features, namely the vertex and the X and Y intercepts, and we understood how we can create families of parabolas just simply by applying combinations of stretching, shifting and reflecting. Okay, and we said, well look, if we get given the quadratic in this form here, and remember we call this completed square form, this is really helpful for finding the vertex, okay? And we can also find the intercepts as well in this form. But generally we get given a quadratic in this form, just because it's easier to write, and actually there are reasons for writing it like this, which will become more apparent as we go along. But this is called general form, so this is usually the form we get given our quadratic in. But it's much harder to find the vertex in this form. Okay, so what I want to look at today is giving you some techniques, some tools in your toolbox, if you like, to help you better work with quadratics, and particularly help you to draw those quadratics and help you to draw those parabolas, even if you get given something in general form. Okay. So before we get going, I actually just want to remind ourselves of how we expand things like this, okay? So if we want to expand something like x plus 3 times by x plus 4, well, I know we've looked at it before, and I know I've kind of drawn in arrows to kind of help you think, well, everything in the first bracket has to meet up with everything in the second bracket. We're literally just applying the distributive law there. You notice that if we work with a quadratic, there's a clue in the name. Okay, you see that in the name this says quad. Now, hopefully you realise that quad just means 4. Think of quadruple or quadrilateral. Just simply means 4. So what on earth has 4 got to do with anything like this? I mean, even if we look at sort of expanded form, sort of general form or vertex form, you notice that the highest thing that we're looking at is really something raised to the power of 2, something squared, okay? That's really what quadratics are all about. So what on earth has 4 got to do with stuff that is being squared? Well, let me just remind you, and I know we've looked at this with indices. If I give you a square, okay? If I give you a square, the reason why I say 5 squared, so if I write that down, the reason why I say 5 squared rather than 5 to the power of 2 is because I'm literally looking at a square with side length 5. Okay, so I'm literally looking at a square with side length 5, and the 5 squared, which of course in this case is 25, is simply saying, well, what is the area of the square with side length 5? So the act of squaring something is looking at the area, in this case of a square. Okay, so if I look at this thing here, well look, I have two things being multiplied together. I have an x plus 3, that's a number, and I'm timesing it with an x plus 2, that's also another number. So if you just think, well, okay, x plus 3, x plus 2, they're different numbers, clearly, because if I stick a value of x in here, x plus 3 is different to x plus 2. Take a number, add 3, that's different to taking that number and adding 2. But I should still be working with the area. Now, if I'm looking at the area of a 4-sided shape, but the side lengths are different, so 2 of the side lengths are different anyway, I should be looking at a rectangle in this case. So if I draw myself a little rectangle, so here we go, there's a rectangle there. It's not fantastic, but it will do the job, okay? Then I can basically break this rectangle up and say, one of the side lengths has got to be x plus 3. So one of the side lengths has got to be x plus 3. And in this case, fairly obviously, it's got to be the longer side. And the other side length has got to be x plus 2. So this is x, and this is plus 2, okay? So if I break this up then, what I'm basically saying is, what is the area of this shape? Well, have a look. X is going to basically be from here to here, okay, and from here to here. So I'm basically saying x is from here to here. The remaining bit is 2 on the vertical side. The remaining bit is 3 on the horizontal side, okay? So it basically means that I can break this up, and I'm just going to break it up very crudely. So this is what I end up with. I end up with this here, which is going to be x squared. You happy with that? Because I have x times by x. I end up with this area down here, which is going to be 2 times 3, so that's going to give me 6, that area is 6. Then I end up with 2 more areas, this area and this area. And basically these 2 areas, well, this area is going to be the 3 times the x, okay? So this area is going to be 3x, and this area is going to be 2 times x. So in other words, I'm going to end up with 2x here, okay? So if I add all of this together, I'm going to end up with x squared plus, well, 3x plus 2x, that gives me an area of 5x plus 6. So you notice that if you didn't like doing the method using the distributive law that I did earlier, that thing is exactly the same as this thing down here. Okay, so you can do it using the grid method as well. Now this is going to really help us, particularly when we're trying to factorize. Okay, so if I wanted to go back the other way, let me show you how I could factorize this. So if I try factorizing, something like this. So if I gave you something like x squared plus 5x plus 6, okay, and if I asked you to factorize this, well, have a think, okay? What I'm basically saying here is I'm starting off with a rectangle. I know it has to be a rectangle, okay? And I know that I'm going to have 4 pieces to the rectangle. Okay, I'm going to have one piece here. Oops, let me just make sure it's straight. I'm going to have one piece here and another piece here. So basically I'm going to end up with 4 pieces, and I'm just going to make that a little bit more obvious. So something like that, okay? Now I know that this piece here is going to be my x squared. I know this piece is going to be my x squared. And I know that this piece down here is going to be what happens if I multiply my numbers together. So I know this is going to be 6. So in other words, this is going to become from x, and this piece is going to become from x. Then I'm looking for something that goes here and something else that goes here. Now I know that my 2 things that I don't know at the moment have to multiply together to make 6. So this times this has to multiply together to make 6. But I also know that this thing here is going to come from this times this, and this thing here is going to come from this times this. So in other words, my 2 unknowns have got to multiply together to make my 6, and I know that my 2 unknowns, these 2 pieces of my rectangle here, have got to add together to make my 5x. Okay, I know that from what I did before, right? So therefore, I'm looking for 2 numbers that multiply together to make 6, and which add together to make my 5, okay? Because that's my 5 from here to here, and this is my 6 being multiplied them together from here to here. So similar to before, hopefully you can break this up. So my 2 numbers is going to be 3 and 2. So therefore this thing here is going to be 3, and this thing here is going to be 2, okay? And that's going to give me, lo and behold, 3x and my 2x, which is going to give me my 5x. So if you wanted to do it using the grid method, that is fine. Now we looked quite a lot a couple of videos ago at factorizing, so whatever method you like, whether you like this grid method or whether you like the method that we used in the last video, which just simply find 2 numbers that multiply together to make 6 and add together to make 5, either one is fine here, okay? And we did also look at solving quadratics as well, in other words, finding the X intercepts. Now, in this video, we're going to look a little bit more at factorizing, but we're going to look at trying to factorize non-monic quadratics. So what do I mean by that? Well, a monic quadratic are the quadratics that we've kind of looked at up until now, okay? So the monic quadratics are just simply quadratics where the first number is just 1, okay? So this is just 1 here. So we're going to have 1x squared, for example, something like 3x plus 4, okay? That's fine. These are monic quadratics because the first number is 1. We call this the leading coefficient. So coefficient, remember, the coefficient, remember, is the number that we multiply by the value of x, the unknown, the variable, okay? So that's the coefficient, and it's leading because it's the one at the front. It's the one attached to the highest power of the term. So in other words, the degree term, okay? So in this case, the x squared, okay? Now, what happens if we have a non-monic quadratic, okay? So what happens if we have a non-monic quadratic like so? Well, if a monic quadratic is where the number in front of the x squared, the leading coefficient, is 1, a non-monic quadratic would be something like this. So 3x squared plus 9x plus 6, okay? You notice here that the leading coefficient is not 1, so mono meaning 1, it's not 1, so it's non-monic, okay? So how do we go about factorizing things like this? So if I give you 3x squared plus 9x plus 6, how on earth do we go about factorizing something like this? Well, in this case, it's not a massive deal, okay? Because in this case, you notice that every single term has a factor of 3 in it. So what I could do is actually turn this into a monic quadratic by factorizing a 3 out the front. So I'd end up with x squared plus 3x plus 2. Okay, so that makes things a little bit easier. So I factorize the 3 out and I just end up with x squared plus 3x plus 2, okay? Which then means that I can just simply focus on the bit inside here, okay? So the bit inside here, if I factorize it, it's going to be x plus 2 times by x plus 1. Just remember, that's exactly the same as what we were looking at before. And I'm just going to make sure that I carry the 3 down. So therefore, if I wanted to fully factorize this, this is going to be 3 times by x plus 2 times by x plus 1. Okay, so that's kind of specific examples, and it's always good to kind of look for examples like that because sometimes they can really help you out. But what if I give you something like this? So what if I give you something like 4x squared minus 11x plus 6? Okay, so this is going to be slightly more tricky to solve because you notice that I can't just simply factorize out that 4. Okay, because the 4 isn't common to the 11 or the 6 either. So what I'm going to do instead, I'm just going to give you the recipe and then I'm going to talk you through why it works. Now just be fair warned, there are different ways of doing this. So if you're not happy with the way that I'm going to show you, please feel free to go away and have a look at other methods, okay? In actual fact, the way that I was taught how to do this was just to factorize it directly. So just simply set up my two brackets and then just see which way it would go, okay? But I'm going to show you a slightly better method that is slightly more reliable than just relying on kind of this. But no matter what method you use, it's all about practice, okay? So the first kind of few times you're like, oh, this is actually really difficult, I'm not making sense of this, and you might make a lot of mistakes. That's fine. Just keep practicing through it, and I promise you, you will get it. It'll become second nature to you. So I'm going to show you the recipe, and then I'm going to show you how we get it, okay? So first things first, I'm going to look, same as before, for two numbers that multiply together to make something and which add together to make something. Now, the adding together is still going to be the same as before. So it's still going to be adding together to make, in this case, negative 11, okay? But the multiplying is not just multiplying to make the 6. In actual fact, in this case, because it's non-monic, it's going to multiply to make 4 times 6. So in other words, I take the leading coefficient here and I multiply it with that last number to find what I need to multiply together to make. So I'll just put it in brackets. So it's 4 times 6, which is going to be my 24. Okay. Now you might say, well, hang on a minute. This is already different to what we did before. Except that it's not, because you notice with the monic quadratic cases, we'd look for two numbers that multiply together to make, in this case, 4. But really, where did that 4 come from? Well, it came from 1 times 4. It's just that 1 times 4 with monic quadratics is still just that last number. So in actual fact, even though it looks like it should be different, it's not, okay? So just remember that you need to multiply these two numbers together, regardless of whether you're looking with monic or non-monic quadratics. It's just with the monic quadratics case, we didn't bother thinking about it like that because 1 times anything is just itself. Okay, so can we find two numbers then that multiply together to make 24 and which add together to make negative 11? Well, let's have a think. Let's first of all write down all the facts of 24, okay? So we can have obviously 1 and 24. We can have 2 and 12, we can have 3 and 8, and we can have 4 and 6. And of course, because it's adding together to make 24, positive 24, we could also have two negative numbers multiplying together to make 24. So we could also have negative 1 and negative 24, or negative 2 and negative 12, or negative 3 and negative 8, or negative 4 and negative 6. So always consider that. Okay, just think that because you've got to multiply together to make a positive number, that means that either both of the numbers are positive or both of the numbers are negative. Okay, if it's multiplying to make a negative, then one of the numbers had to be negative. So just remember that we always have to consider the negative cases as well. Okay, now just have a look. I effectively have 8 sets of factors here. Now, which of these sets of factors add together to also make negative 11? Well, I think the ones that you want are negative 3 and negative 8, because negative 3 plus negative 8, that makes negative 11. Okay, so I'm looking for negative 3 and negative 8. That's the set of factors that I'm after. Now, what do I do with that set of factors? Well, if I come back over here, I'm just going to copy down my 4x squared, and I'm just going to copy down my last term, which is my positive 6. And what I'm going to do is I'm just going to split my 11x up, or my negative 11x up. Now you notice I can split this up however I like. Like negative 11x just simply means negative x 11 times. Okay, so just imagine like a negative x, another negative x, another negative x 11 times. That's what a negative 11x is made up of. So I could split that up however I like. And I'm just going to group it the way that I've been told to group it here. In other words, into negative 3x's and then negative 8x's left over. Okay, so negative 3x's and then negative 8x's here. You notice that is still negative 11x. Negative 3x minus 8x, that is still negative 11x, okay? Now what I'm going to do is I'm going to draw an imaginary line down the middle. Now, I say it's imaginary. I've drawn it, okay? So I have drawn it in, but it doesn't matter, okay? So I've just simply drawn a line down the middle just to kind of separate the two sides of this equation. So on one side of the equation, or the expression rather, I have the x squared term and an x term, and the other side of the line, I have an x term and a constant term. Now my job now is to factorize, and I mean fully factorize, both sides. Okay, so I'm looking for a common factor which appears on both sides of this expression. So let's first of all focus on the left-hand side. Okay, I want to try and factorize this. So if I'm going to try and factorize this, well, 4x squared take away 3x. The thing which is in common to both of these sides, on the left-hand side, is an x. So I'm going to factorize the x out. So if I factorize an x out of the left-hand side, I'm going to be left with 4x minus 3. Okay, so that's just simple factorizing, simple, straightforward factorizing. Now, whatever happens, what I've got on the left-hand side, so this 4x minus 3, I must also have that as a factor on the right-hand side as well. So I must also have a 4x minus 3 in brackets on the right-hand side as well. So that's really important. Once you've got a factor on the left-hand side, you must also have it on the right-hand side as well. So now let's have a look. Let's have a look here. Okay, so the number which is going to go here has to give me, when I expand this thing out, it has to give me my negative 8x plus 6. So let's think, what number times 4x is going to give me negative 8x? Well, isn't that negative 2? Okay, isn't that negative 2? And let's just quickly check. What number times negative 3 is going to give me positive 6? Lo and behold, negative 2 times negative 3, that makes my positive 6. So there we go, okay? This is kind of the hardest bit done. Now, just a word of warning. If you end up with a bracket here and a bracket here, and if you can't figure out how to get this side, once you've got that bracket, it's probably because you haven't factorized enough on the left-hand side. So always have a look at the left-hand side and make sure you fully factorized. So don't just pull out an x, sometimes it'll also be a number which is in common to both as well, okay? Okay, fine. So let's finish this off then. So basically what I'm left with, if I get rid of this imaginary line down the middle now, basically what I'm left with is this. So x times by 4x minus 3 minus 2 times by 4x minus 3. Well, the thing which is in common to both the x term and the negative 2 term is the 4x minus 3. So I'm going to factorize that out. I'm going to factorize out 4x minus 3. What am I going to be left with? Well, I'm just going to be left with the x minus 2. Okay, because I've literally just factorized out the 4x minus 3. So this would be it fully factorized. So 4x squared minus 11x plus 6, this is the thing I started off with, fully factorized would be 4x minus 3 times by x minus 2. Okay, so this will be fully factorized. Let's see this happening with another example then. So let's have a look at this then. Let's follow exactly the same thing as we did before. You notice this is a non-monic quadratic. It's just it's a quadratic in k this time. So you notice that I'm using k squareds and k's here instead of x's. That's totally fine. It still works in the same way. Okay, so it's non-monic because the leading coefficient is not 1. So now let's figure out how we should deal with this. So it's exactly the same thing as before. Okay. So first things first, I need to look for two numbers which multiply together to make, well, now we need to be careful because it's not multiplying together to make 5, we're multiplying together to make 6 times 5. Okay, so we're multiplying together to make 6 times 5, which is 30. So that's what we need to multiply together to make. And they need to add together to make negative 17. Okay. All right, so let's just list. Well, if we're dealing with 30, I think we can do this slightly quicker. I think it's going to be something like 15 and 2, but because we want negative 17, it's going to be negative 15 and negative 2. Okay, so you can either just write out all of the different factors, or if you're slightly quicker and more able with this, have more practice with this, you can just sort of think about it directly. Okay, so you can have them visualized in your head instead. So just think. First things first, we're going to break up, or we're going to write the 6k squared and the plus 5 down. We're not changing that, but what we are changing is the negative 17k. Okay, and we're breaking it up into negative 2k and negative 15k. So I've still got negative 17k in the middle. It's just I've broken up in different order. Notice it doesn't matter what order they come in. All right, fine. So now I'm looking at this and I'm thinking, I'm going to split it down the middle. So I'm just going to draw my imaginary line in. And I'm going to look first of all at the left-hand side. Now, if I'm going to factorize this, absolutely we can factorize a k out. But be careful because we can also factorize out a 2 as well, because 2 is common to both 6 and 2. So if we factorize out a 2k, Then in the bracket, we're going to end up with 3k minus 1, okay? Now, whatever happens, we need to have exactly the same bracket on the right-hand side, so the 3k minus 1. Now let's have a look at the right-hand side, okay? So I'm basically looking for a number here, which when I multiply it with the 3k minus 1, will give me negative 15k plus 5. So let's break it down, okay? What number times by 3k gives me negative 15k? Well, hopefully you're happy, it's going to be negative 5. And just check, what number times by negative 1 gives me positive 5? Well, okay, negative 5 times negative 1, that's also going to give me positive 5 as well. So there we go. That would be it fully factorized. So, or not fully factorized, but that would be it sort of at that stage there. So now all I need to do is think, right, I've got a 3k minus 1 on both sides, and that's common, so I'm going to factorize it out. So I'm going to factorize out 3k minus 1, and I'll be left with 2k minus 5. Okay, so in other words, what I'm saying here is that if I start off with 6k squared minus 17k plus 5, that will factorize to 3k minus 1 times by 2k minus 5. And there we go. So that would be it fully factorized. All right, fantastic. So, okay, why is this useful? Why is it useful to be able to factorize quadratics? Well, let's suppose I give you a quadratic that looks like this, okay, and I ask you to sketch it. So let's suppose I ask you to sketch something like y equals 2x squared minus 5x minus 3. Okay, so let's suppose this is a quadratic that I want you to sketch. Now just remember, one of the first places to start if I want you to sketch it is to first of all think, right, is it a happy face or is it a sad face quadratic? Well, hopefully you realize, and this was based on what we were doing in the last video, what I mean by happy face and sad face, first of all, is it this way up or is it this way up? Okay, so is it that way up, so this would be y equals x squared, or is it this way up, which is y equals negative x squared? Okay, maybe if I do that in a different color to make it a bit more obvious. This one would be negative x squared. So what I mean by happy face and sad face, hopefully you can see. Happy face would be y equals positive x squared, and a sad face would be y equals negative x squared. Now, fortunately, we were able to establish that really easily just by looking at the leading coefficient. Remember, this is based on what we're doing with our stretch. Because effectively, that leading coefficient, the thing which we multiply by the x squared, is going to tell us what type of stretch it is. Okay? If it's a positive number, it means it stays positive. It means it stays happy. Whereas if it's a negative number, it means it stays sad. So in this case, because that is positive, because the leading coefficient is 2, it's not negative 2 or something, it means that it stays positive. In other words, we're looking at a quadratic that looks something like this. So it's got to have a happy face. Now I need to establish what are the intercepts. Now, in order to establish the intercepts, let's go first of all go for the y-intercept. So in order to get the y-intercept, just remember that I set x to be 0. So let's see what happens if I set x to be 0. So I get 2 times by 0 squared minus 5 times 0 minus 12. So let's have a look. Well, 2 times 0 squared, well, that's 0. Minus 5 times 0, that's 0. And then take away 12, well, okay, I get y equals negative 12. So that there is going to be my y-intercept. So I know it's going to cross the y-axis at negative 12, okay? But if I want to find the x-intercepts, what do I need to do? Well, to find the x-intercepts, I need to set y to be 0, okay? So if I take my original graph, my y equals 2x squared minus 5x minus 12, that's my original quadratic. If I set y to be 0, I get 2x squared minus 5x minus 12 equals 0, like so, okay? Now I need to try and solve this. Now, are you happy that using kind of traditional sort of algebra, like adding 12 to both sides and then trying to divide or multiply by numbers, it's not going to get us very far, okay? Try it yourself. I can promise you won't get very far. So what we need to do instead is we need to employ the techniques that we've done in the last sort of few videos, namely factorizing. So let's try actually factorizing this thing. So first of all, we're looking for two numbers. It's non-monic, so we're looking for two numbers that multiply together to make 2 times negative 12. Or negative 24. And we're also looking for those same two numbers to add together to make my negative 5. Okay, so add together to make negative 5. All right, so let's think. Two numbers multiplying together to make negative 4, and which add together to make negative 5. I think 8 and, so negative 8 and positive 3 would work there. So negative 8 and positive 3. So again, the only reason why I came up with those so quickly is because I'm practiced with them, knowing your times tables, right? But yeah, if you didn't know how to do that, just literally write down all the factors of negative 24 and then just see which of those add together to make negative 5. So what that tells me then is that when I rewrite this equation, so 2x squared, I'm going to keep 2x squared the same, I'm going to keep the negative 12 the same, and I'm going to keep the equals 0 the same. However, I'm going to break negative 5x into negative 8x and positive 3x. So negative 8x and positive 3x. It's still negative 5x in the middle. The thing in red is still negative 5x. It's just I've broken it up into my two parts. Now what I'm going to do is draw the line down the middle. Okay, so if I draw the line down the middle, it means that I factorize what's happening on the left and I factorize what's happening on the right. So here we go. If I factorize the 2x squared minus 8x fully, I can factorize out 2x and I'll be left with x minus 4 here. Okay. Now whatever happens, I must have the x minus 4 on the right hand side as well. Okay, so now I just need to think, right, what number times x is going to give me positive 3x? Well, fairly obviously, it's positive 3. And just check, does positive 3 times negative 4 give me negative 12? Yes, it does. Okay, so that works. So just remember, I also need to keep the equals 0 now, because remember, I have not changed the equals 0 at all. So it's all equal to 0. Now what I need to do is fully factorize this. So in other words, I can factor out the 2x plus 3 from the x minus 4. I'm factorizing out x minus 4 from both the 2x term and the 3 term, and remembering that's all equal to 0. Now ordinarily that would be it, that would be finished, that would be it fully factorized. But in this case I actually want to find my values of x, I actually want to find my x intercepts. So in order to find my x intercepts I need to try and solve this thing. So how can I solve it? Well, first of all, you notice that I have two things being multiplied together and they equal 0. So therefore either the left hand side, the 2x plus 3 has to equal 0, or the right hand side, the x minus 4 has to equal 0. Okay? So it's really important there, because I've got two things being multiplied together and they equal 0, at least one of those things has got to be equal to 0. So either 2x plus 3 or the x minus 4. So if I solve this, I have 2x plus 3 equals 0. Well, that's going to give me x equals negative 3 over 2, or negative 1.5 if you prefer. Remember, how did I get that? I just simply take away 3 from both sides. In fact, let me write this down properly. I take away 3 from both sides, so I get 2x equals negative 3, and then I divide both sides by 2. So I get x equals negative 3 divided by 2. So that's one of my values of x, negative 3 over 2. Okay. The other value of x which I'm looking for, I get from solving this equation here. Just remember, I get that just by adding 4 to both sides. So x, if I add 4 to both sides, I get x on the left-hand side and 0 plus 4 on the right-hand side, or x equals 4. So that there would be my second solution. Okay, so what do these correspond to? Well, these correspond to my x intercepts. So just remember, my original y intercepts all the way up here was y equals negative 12. I established that it was a positive quadratic, or positive face, because the leading coefficient is positive. And I've just found my x intercepts here. So let me just write down those three pieces of information. First of all, it's a positive quadratic. In other words, it's a graph that looks like this. Okay, I found that my y-intercept is negative 12. Okay, I found that all the way up here. Okay, negative 12, just by setting x to be 0. And I've just found that my x-intercepts are x equals negative 3 over 2, or x equals 4. Okay, so I'll just write that's y equals negative 12. So these are the three pieces of information I need. Now I'm in a position where I can actually try and sketch this thing. Now what I would always recommend that you do first of all is sketch yourself the graph, the shape of the graph first. So it's a positive quadratic, so I'm just going to draw myself in a positive parabola. In fact, I should put parabola up here. So I'm going to start off by sketching myself a positive parabola. Then I'm going to try and make the axes fit the parabola, rather than the other way around. Most people draw the axes first and then try and make the parabola fit the axes. And that's much harder to do. It's much easier to draw a nice smooth parabola and then try and make the axes fit that. So first of all, I know it intersects in two places. And I've just got to think, well, okay, if it intersects there and there, I'm just going to draw my x-axis in and make sure the x-axis is obviously straight. Like so, or relatively straight. Okay, so I'm going to draw my x-intercept. So I know one x-intercept is negative 3 over 2, or negative 1.5 if you prefer. and the other x-intercept has got to be at x equals 4. Okay, so those are my two x-intercepts. Now I've just got to work out where is my y-axis going to be. Well, my y-axis has obviously got to be between negative 3/2 and positive 4, because obviously the x-axis, the y-axis is when x equals 0, right? So I've just got to think, right, where is x equals 0 on this scale? Well, you're happy it's going to be closer to negative 1.5 or negative 3/2 than it is to x equals 4. So in other words, I think it's going to be about there. So in other words, I'm just literally going to draw this in. So this is my y-axis now, which I'm drawing in, like so, okay? And I'll just plot the origin point there. And that there would be a perfectly good parabola. Okay, I've sketched the relevant points. Only thing I'm missing is this intercept here. So this is going to be y equals negative 12, because I worked out that was my y-intercept. This is negative 12, all right? So that there would be a perfectly acceptable sketch. Except there's one more piece of information that we can plot on this graph, and we looked at this in the last video. The other piece of information we need is this thing here, which you remember is called the vertex. Now, the vertex is really easy to read off if we have it in the form, the completed square form. So remember the completed square form, did it right at the very start, all the way up here. Okay, this is the completed square form here. This is the completed square form. So we need it looking something like this. Okay, now at the moment, the thing which we've got is not looking anything like that. Okay. The thing which we've got is actually looking more like y equals, where is it? Here we are. Y equals 2x squared minus 5x minus 12. This is in general form. So the next thing we need to look at is think, right, okay, we've just realized from this general form, we can find the y-intercepts and x-intercepts just by setting either x to be 0 or y to be 0, and we can factorize. But now we need to think, is there another way now of converting this from general form into completed square form? And the answer is yes. So one reason why we prefer completed square form sometimes over general form is because completed square form is really easy to read off where the vertex of a parabola is going to be. In fact, in general form, in this sort of general sort of case with p's and q's and r's, which just represent numbers, the vertex is going to be at negative q, positive r. Okay, so that's a really easy way of reading off where the vertex is going to be. The other reason why we like completed square form is because if we're given a quadratic in general form, and if we can't factorize it. So for example, if I give you something like y equals x squared plus 8x plus 2, and I ask you, find me the x-intercepts, or find me the, sort of factorize this to find the x-intercepts. So if I factorize it, well, okay, I'm looking for two numbers which multiply together to make 2. So something times something has to give me 2, and something which adds together to make 8. Well, have a think. Two numbers multiplying together to make 2, adding together to make 8. I can't think of any off the top of my head, okay? Well, fortunately, if we can find a way of getting from general form into completed square form, it kills two birds with one stone. Number one, if it's in completed square form, we can always find the vertex. And if it's in completed square form, we're also able to deal with things that can't be factorized. In other words, we're able to find the x-intercepts for things that can't be factorized. So let's have a look. How do we go from general form to completed square form? Now the key is with these really cool things called perfect squares. So perfect squares are kind of really nice. They're really kind of a good feature of mathematics, okay? And particularly in quadratics as well. So the reason why we call them perfect squares is because we have something that looks like this. So if I give you something like this, x plus 4 all squared, okay? Now if I expand this out, if I expand out x plus 4 all squared, then would you be happy, this could be treated as x plus 4 times by x plus 4. And if I expand it, well, I've got x plus 4 times x plus 4. If I expand that very quickly, I'll get x squared plus 8x plus 16. So this is called a perfect square. The reason being is because rather than factorizing to two different brackets, like x plus 2 times x plus 3, or something like x minus 1 times x plus 100, okay, it factorizes just one bracket which is the same. So x plus 4 times x plus 4, or we can write that as x plus 4 squared, okay? And the key is, and the reason why we call it completed square form, is because we are trying to turn something which isn't a completed square, a perfect square, into something that does look like a perfect square. So in other words, we're completing the square, okay? So let me show you a little bit more with a few more examples. So if I start off with x plus 1 all squared, hopefully you can expand this out for me. So I'll just do it very quickly, but if you wanted to pause the video and actually have a go at expanding this yourself, just think about it as x plus 1 times x plus 1, and you'd end up with x squared plus 2x plus 1. Okay. Now if I work with something like x minus 1 all squared, so another perfect square, x minus 1 all squared, and if I expand this out, I'll get x squared minus 2x plus 1. Now if I work with something like x plus 2 all squared, well, this is going to give me x squared plus 4x plus 4. And if I work with x minus 2 all squared, this is going to give me x squared minus 4x minus 4, sorry, plus 4. If I work with x plus 3 all squared, this is going to give me x squared plus 6x plus 9. And if I work with x minus 3 all squared, this is going to give me x squared minus 3x plus 9. So basically the reason for doing that, the reason for doing those six expansions of perfect squares, is because I want you to notice the pattern between the expanded form, because this looks a bit more like general form, and the factorized form. So what's the pattern between the two things? Well, first of all, you notice that the x just appears in all of them. So the x is at the start of each of the brackets, and we've also got the squared afterwards. So in other words, when we're trying to do this, so if I would take, say for example, x squared plus, if I take something like x squared plus bx plus c, and if I'm trying to factorize this, okay, if I'm trying to factorize this, you notice first of all that this number here has a connection with both the 2 and the 1 in this case, okay? And likewise, this number here, the negative 1, has a relationship between the negative 2 and the positive 1. And I want you to tell me, what is the relationship between those two numbers, okay? Well, first of all, you notice that the number over here, so the positive 1 or the negative 1, whatever it might be, is always half of whatever goes in the middle, okay? So the number that goes inside the brackets, okay, is always half of whatever appears over here on the right hand side. So in other words, if I'm trying to factorize this thing here, then I'm just going to end up with x plus, and I've got to halve that thing there, so the b over 2. So I've got to halve that thing there, okay? But you also notice that there is a relationship between this number, so the number that goes inside the brackets, and this number here. This number is always the square. Okay, so this number here is always the square of whatever appears inside the brackets. Okay, so let me just show you that. Okay, so this thing here, whatever appears over here on the left-hand side. Okay, so let me get rid of this actually. So if you have a look at the relationship between these two things, okay, you have a look at the number inside the brackets. In this case, it's negative 1. Well, the negative 1 is always half of whatever goes here. So half of negative 2 is negative 1. That works. But then this negative 1, the thing that appears inside the brackets, is always the square of whatever appears last. Okay, so this is always going to be true. Okay, the number that goes in front of the x is always, you need to halve it to find out what goes here. And then you need to square the number inside the brackets to find out what goes here. So just think, halve it, square it. Halve it, square it. Let's see that pattern continue. So this positive 4, you halve it, you get positive 2. You square that positive 2, you get your positive 4. Okay? If you take the negative 4 in this case, you halve it, you get negative 2. You square the negative 2, you get positive 4. Okay? Keep going. If you take the positive 6, halve it, you get 3. Square it, you get the positive 9. Okay? And the same is also true for the last one. So in other words, the relationship between the factorized perfect square and the expanded perfect square, the thing inside the brackets is always half of whatever the coefficient of x is, so half of that middle term, and the last number of the expanded form is always the square of whatever appears inside the brackets. Okay, so that's a really important feature that I want you to notice. So in other words, if I give you something that looks like this is expanded at the moment, and if I want you to turn it back into its perfect square factorized form, you can basically see, well, okay, I need to put it into a bracket, I need to square it, put the x at the start. Then the number that goes here is going to be half of whatever goes here. So half of 8, that's 4, so it should be a positive 4 that goes there. But then I just need to check that the square of whatever goes here will give me 16. Well, 4 squared, that gives me 16. That works, okay? That works. So what if I give you something like this instead? So if I give you something like x squared plus 8x, but this time I give you plus 2. Now clearly this isn't going to be a perfect square, because the perfect square of x squared plus 8x plus 16 is x plus 4 all squared. But that's okay, because I can make it look a bit more like a perfect square. And the way that I'm going to do this is actually just stick in an equals 0. Okay? Because the thing which is going to screw this up is actually that last number there, that last constant term. So in other words, I want to get rid of that last constant term. So the way which I'm going to do it is just by taking away that constant term. So it's out the way. Now, if you're comfortable with just thinking about it as out the way, that's fine. But in this case, I'm actually physically going to take it over on the right-hand side. I'm going to take away 2 from both sides. Then I need to figure out, well, what is the number that goes here? So have a look. If I'm going to factorize the left-hand side, ignore the right-hand side for the time being, okay? If I'm going to factorize the left-hand side, well, first of all, let's set it up. So x plus something all squared, or minus something all squared, okay? But then the thing which goes here has always got to be half of whatever the x term is. So the half of the 8, that's going to give me the positive 4. So I know it should be positive 4 here. However, what should be appearing here is got to be the square of whatever appears there. Sorry, whatever appears up here. So what should be appearing up here should be the square of whatever's inside the brackets. Well, the square of inside the brackets is going to be positive 16. So I'm expecting a positive 16 here. But of course there wasn't a positive 16 there, so I'm going to do it on both sides. Okay, that just basically balances it out. Because as long as I do the same thing to both sides, I haven't changed the value of this equation. Okay, so I'm just adding 16 to both sides, then I know that the left-hand side is a perfect square. Okay, but then if you have a look, what am I left with on the right-hand side? Well, negative 2 plus 16, that's going to give me positive 14. Okay, now you notice that originally, my original kind of thing that I dealt with didn't have the equals 0, didn't have an equals in at all. So all I'm going to do, just to make sure I keep the equals balanced, or rather to get rid of the equals 0, I'm just going to take away 14 from both sides. So I'm going to end up with x plus 4 all squared, take away the 14. Okay, then I would have equals 0, but remember, I didn't have the equals 0 to start off with, so I'm not going to bother writing it. So in other words, what I'm saying here is that if I start off with x squared plus 8x plus 2, if I want to put this into a completed square format, in other words, something that looks like a perfect square, I need to write it as x plus 4 all squared, take away 14. Okay? Now you notice that that is really useful because we've looked in the last video that if we get given something that looks like that, it's really easy to read off where the vertex is going to be. In this case, it's going to be negative 4, negative 14. Okay? So let me just recap this because it's really important. Effectively, what I'm doing here is I'm looking to complete the square. I'm looking at the first 2 terms. I'm looking at those 2 terms there, and that is going to tell me what appears inside the brackets. Namely, I just take the 8 and I halve it to see what goes there. But then I need to make sure that I take away whatever I'm adding on because it wasn't originally there. Okay? So in other words, if I'm going to expand out x plus 4 all squared, I'd end up with x squared plus 8x, but then I'd get this 16, which I don't want. So in other words, I need to take away 16 to ensure that I get the x squared plus the 8x. Let me show you with another example. So let's take something like x squared minus 10x plus 4. Okay, so let's start off with something like this. So complete the square, I need to look at the first 2 terms, the x squared minus 10x. Well, okay, if it was just x squared minus 10x, I would expecting a completed square or a perfect square to look something like x minus 5 all squared. Okay, you happy? Because I just simply halve that 10, or half the negative 10 rather. Okay, but I can't just deal with it like that because, of course, if I was going to expand this out, it's going to give me x squared minus 10x, which is exactly what I want, but then I'm also going to get plus 25, which is what I really don't want. So if I expand out the x minus 5 all squared, this is what I'm going to end up with. But I don't want the positive 25 there. So what I'm going to do is I'm going to take away 25. Because of course if I take away 25, those 2 things cancel, and I'm just going to be left with the x squared minus the 10x, which I wanted at the beginning. So in other words, the thing in red The thing in red, the x squared minus 10x, I can factorize that to as a kind of completed square or perfect square as x minus 5 all squared minus 25. But of course, the plus 4 still comes down for the right. That hasn't changed places at all, so it's still there, okay? So now I can fiddle around with this and I can say, actually, if I just deal with the minus 25 plus 4, that's going to give me my minus 21. So it should be x minus 5 all squared minus 21. Let me show you with another example, okay? So let me show you with something like x squared minus 12x plus, let's make it minus this time. Let's make it minus 3, okay? So, okay, to complete the square, I'm only interested in looking at the first two terms. So in other words, if I was going to put this into perfect square, it would be something like x minus 6 all squared. However, the issue is x minus 6 all squared is not going to work because I'd get the x squared, I'd get the negative 12x, but I'd also get a positive 36 because I'd have to end up squaring the negative 6 to get positive 36. I don't want that. I don't want positive 36, so therefore I'm going to have to take away the 36. Now, this thing in red, so this thing here, is the same as x squared minus 12x. I've made it the same as. The negative 36, if you like, is a bit like a fudge factor. Okay, but obviously the negative 3 just comes along for the ride. That's all I'm doing there. Okay, so there was the thing in red, the x minus 6 all squared. Let's put it in red. Take away 36. That is exactly the same as x squared minus 12x. Expand it out if you're not sure. It definitely is. Then the negative 3 just comes along for the ride. Then all I need to do, just to tidy this up, still have the x minus 6 all squared, but negative 36 minus 3, that's going to give me negative 39. Okay, so hopefully that makes sense. Let's just see it with one more example. Let's see it with something like x squared plus 60x plus 4. All right, so something like this. So first things first, I'm going to focus on the first two terms. Let's see how quickly we can do this. So I'm going to end up with x plus 30 all squared, because of course I need to halve that 60x. But then I'm going to need to take away whatever 30 squared is to make sure I still get the x squared plus 60x. So 30 squared is going to be 900, so I need to take that away. Then the plus 4 just comes along for the ride. Okay. Now I just tidy it up, so I'm going to end up with x plus 30 all squared, and then negative 90 plus 4 is going to be negative 896. Okay. Now the really important thing with doing that is I'm now able to put it into completed square form, which means I'm able to read off the vertex. Okay, so let's go back. What's the vertex of this parabola here? Well, the vertex is going to be 5, negative 21. What's the vertex of this parabola going to be? Well, the vertex is going to be 6, negative 39. What's the vertex of the parabola we just looked at going to be? Well, the vertex is going to be negative 30, negative 896. So now I can put something in completed square format. It's really easy to read off where that vertex is going to be. Now let's generalize this, because the trouble is, this is fine if it's monic. So all the examples we've looked at so far are monic. What happens if it's non-monic? So what happens if I give you something like 2x squared plus 8x minus 3? Okay, so what happens if I ask you to complete the square on something like this? Well, the thing is, I know that the first two terms are what are going to tell me what my perfect square is going to look like. Okay. Now at the moment, I don't know how to deal with the non-monic. I don't know how to deal with this 2 out the front, but that's okay. Let's just deal with it to see what it would be if it was just a 1 out the front. In other words, let's factorize out a 2 from the two terms that we need. Okay, so I'm looking for the 2x squared and the 8x. I need to factorize out a 2 to see what I'm left with. Okay, so if I factorize out 2, then I'll be left with something that is monic. Okay, so x squared plus 4x. Then the minus 3 just comes along for the ride. So the reason why I did that is because now I can just focus on these two terms here to tell me what the completed square term is going to be. So if I focus on those two terms, ignore everything else, just literally look at x squared plus 4x. Turn that into a perfect square, or something that looks like a perfect square. That's going to be x plus 2 all squared. But then I'm going to have to take away 4. Okay, because I don't want that plus 4 at the end, so I'm going to have to take it away. Then I'm just going to put everything else in around it. So I'm going to put the 2, I'm going to put the bracket, and I'm going to put the minus 3. So now what I'm going to do is multiply out the 2 over both things inside the brackets. So 2 times by x plus 2 all squared is going to be 2, you guessed it, times by x plus 2 all squared. Don't expand it, because remember, I want the x plus 2 all squared, right? And then I'm also going to have to do the 2 times the negative 4, which is the negative 8, and I'll just have the negative 3 hanging around at the end. Tidy it up slightly, I end up with 2 times by x plus 2 all squared, then that's going to be minus 11. Okay, so again, where's the vertex going to be? Well, it's going to be at negative 2, negative 11. You notice that having the 2 being multiplied at the front, that's just simply going to give a stretch. And as we've seen in the last video, putting that stretch in is not going to change the position of the vertex. Okay, it's just going to be a bit more skinnier than what it was before. Let me show you this with another example. Okay, so let's take, for example, something like 3x squared plus 30x plus, well, let's change it to a minus, doesn't really matter. Let's change it to minus 1. So let's deal with something like this. So again, the 2 terms I'm interested in when I'm completing the square are the first 2 terms. Let's start off by making this a monic quadratic. So in order to do that, I'm going to have to factorize a 3 out. So I'm going to be left with x squared plus 10x. Then the minus 1 just hangs around at the end. All right, so now I'm just going to focus on the bit inside the brackets. I'm going to focus on the x squared plus 10x. Pretend like nothing else is there. Just focus on the x squared plus 10x. Ignore everything else. If I'm going to turn this into a completed square, I'm going to get x plus 5 all squared, but then I'm going to have to take away 25. Okay, so that bit there is equivalent to the bit which I've sort of highlighted in blue. Then I'm going to put everything else in around it. So I'm going to have the 3, and I'm going to have the minus 1. So now what I need to do is expand this bracket out. So I have 3 times by x plus 5 all squared. So that's going to be 3 times by x plus 5 all squared. But then I'm also going to have the 3 times by the negative 25. Well, 3 times negative 25 is negative 75. Then the negative 1 just comes along for the ride. So now just the final bit of tidying. I end up with 3 times by x plus 5 all squared. Then negative 75, take away 1. That's going to be negative 76. Okay. So in other words, the vertex of this parabola is going to be negative 5, negative 76. Okay, let's just do it with one more example. Let's try something like 4x squared plus 18x plus 2. Okay, so this one might end up being slightly more awkward because I'm going to basically be halving a non-square number, but I think it'll be okay. I think it'll be okay with this. So first of all, the 2 terms I'm interested in when I complete the square are the first 2 terms. So let's focus on that and let's make it a monic quadratic. Okay, so in order to do that, I need to factor out a 4 from the front. So x squared, and if I take 18 and divide it by 4, well, that is going to be 9 over 2. Okay, so that's going to be 9 over 2 times by x. So again, it's the same process I was doing before. It just might get a little bit awkward because I'm dealing with fractions, but I think we'll be okay. Now the thing which I'm interested in is the bit inside the brackets. I need to turn that into a completed square. So I'll have the 4. Well, actually, let's just do it with the blue bit first. So if I deal with x squared plus 9x and I turn that into a completed square, well, I'm going to end up with x plus, and remember the thing which I'm adding on is going to be half of whatever the term in x is. So what's half of 9 over 2? Well, half of 9 over 2 is 9 over 4. So that goes there. Then I need to take away the square of whatever goes here. So remember, I've halved it, now I need to square it. Okay, so if I square this, I square the top to get 81, square the bottom to get 16. Then I just put everything else back in its place. So I put the 4 there, and I put the plus 2 there. Now I expand it out, okay? So I take the 4, and I multiply it by the first term, so I get 4 times by x plus 9 over 4 all squared. And I also get that 4 times by the second term. So 4 times by negative 81 over 16. Stick it in your calculator if you're not sure, but it's going to be negative 81 over 4. Okay? And I'm just going to have to add on 2 there. Well, adding on 2 is a bit like adding on 8 over 4. So that's going to give me 4 times by x plus 9 over 4 all squared minus, that's going to be negative 73 over 4. I believe, if I've done my maths correctly, which hopefully I have. I'm always a little bit sort of nervous about doing maths in public, or so at least heavy algebra and fractions and things like algebra in public. Not my favourite activity at all, but I think that's okay. All right, fine. So where's the vertex? Well, the vertex is just going to be negative 9 over 4 and then negative 73 over 4. Okay, so I'm just reading that off directly from that completed square format. Okay. So that's kind of dealt with the first thing that I kind of had a problem with before. The first thing was, well, how do I actually find the vertex of a parabola? Well, I've just shown you how to do that now. You just basically use this process called completing the square. But you remember that I said that there was another reason why I wanted to use completing the square. And the reason was, if something doesn't factorize. So if I deal with a quadratic that doesn't factorize and I'm trying to find the roots, I'm trying to find the x-intercepts, then I can use completed the square in order to do that. So let me show you how I can do that now. So I'm going to just start off with a nice general quadratic. Okay, so I'm going to start off with y equals ax squared plus bx plus c. And let's suppose I want to find the roots. Okay, so remember the roots, another word for these are the x-intercepts. Okay, so to find the x-intercepts, I'm going to have to set y equal to 0. Okay, so starting off with a general quadratic where a, b and c are just general numbers. So for example, I could have something like y equals 3x squared plus 4x minus 2. Okay, I could end up with something like that. So a in this case would be 3, b would be 4, and c would be negative 2. Okay, I could definitely work out how the roots are. So I'm just going to do it in the general case. Then it means that it will apply to every single different type of quadratic that I could ever throw at you. Okay, so first of all, I need to set y to be 0. So I'm going to have ax squared plus bx plus c. That has to equal 0. Okay. All right, fine. So first things first, what I'm going to do, I'm going to try and complete the square on this. Now, because I've got it equal to 0, all I'm just going to do is get rid of this a. So in order to get rid of the a, I'm just going to simply divide everything by a. And then I'm going to end up with a monic quadratic. Okay, so in other words, I'm going to end up with ax squared divided by a, or just x squared. I'm going to end up with b divided by a times x. And I'm going to end up with c over a. And that's got to equal 0, because remember 0 divided by a is still equal to 0. Okay, so far so good. All I'm just literally doing is getting rid of whatever appears at the front. So divide that by a. Okay. All right, fine. So actually, because I want to complete the square on this, I am going to take this c over a over on the right hand side. I'm going to get rid of it. All right. So I'm going to do that by taking away c over a. So I'm going to end up with x squared plus b over a times x. And I'm going to take the c over a on this side. So it's going to become minus c over a. All right, fine. So far, so good. So all I've done at the moment is just literally made the quadratic monic and just taken the c over a term on the other side, so it's out of the way. So now if I just give you this and ask you to complete the square on it, I'm only interested in looking at these two terms here. That's enough to find out what the completed square version or the perfect square version of the left-hand side is going to be. So remember, in order to complete the square, I need to halve whatever goes here. So I'm going to have to halve this number. Well, half times by b over a is going to be b over 2a. All right, so b over 2a. I'm going to have to square it. Okay. Now, of course, I'm also going to have to put a correction term here because it's not going to be quite the same as this in general. I'm going to have to take away whatever this thing is squared. So remember, I halve it, then I square it to find what I take away. So square the top, b squared. Square the bottom, well, 2 squared is 4, and a squared is just a squared. Okay. Now I've still got the negative c over a on the right hand side. Okay, so at the moment I've halved it and then I've squared it to sort of get this in completed square format. So at the moment the bit in green, or the bits in green, are the same thing. Okay, so those two things are the same as each other. All right, good, fantastic. Now, just because I can, and just because ultimately what I want to do is end up with the x-intercepts. Okay, I want to end up with the x-intercepts. So in other words, I want to get x is equal to some value, or x is equal to another value. Okay, so that's what I'm after. I'm after the x-intercepts. So now I'm in this form, okay, I want to get x on its own. So in other words, I want to rearrange this equation to get x on its own. So in order to do that, I'm just going to take everything else over on the other side. So including, first of all, this negative b over a, b squared over 4a squared. Okay, so first things first, I'm going to take this on that side. So on the left-hand side, I'm going to be left with x plus b over 2a, all squared. And on the right-hand side, I'm going to end up with, well, if I add b squared over 4a squared to both sides, then I'll get b squared over 4a squared minus c over a. All right, fine. So far, so good then. I'm just going to work on this right-hand side slightly. So I'm just going to work on this thing here because I don't really like it being two separate fractions. I want to simplify it so it's just one fraction. So if I want to simplify it so it's one fraction, I need the same denominators on both. So, okay, I'm going to keep b squared over 4a squared. I think we can turn this fraction into a 4a squared, okay? And the way to do that is by multiplying this fraction by 4a over 4a. okay? Because notice that on denominator then, I'll end up with 4a squared, and on numerator I'll end up with c times 4a, which is going to be 4ac, okay? Now you notice that because now I've got the same denominator on both fractions, I can just really easily just do b squared minus 4ac, sorry. That's just going to take away the numerators and all over the denominator of 4a squared. That's just simply dealing with algebraic fractions, and we did that in the first week, okay? So in other words, I end up with x plus b over 2a on the left-hand side, all squared, on the left-hand side, and then b squared minus 4ac all divided by 4a squared on the denominator of the right-hand side. So now I think we're in a position, remembering that I'm after x on its own, so now I think we're in a position that we can make this slightly easier. So first things first, I'm going to square root both sides. I'm going to get rid of this square, okay? Now of course I've got to be careful here, because if I square root both sides from something that was squared, I need to ensure that I take the positive or negative root. So I'm going to take the plus or minus root of b squared minus 4ac all divided by 4a squared. Okay, I'm going to take the square root of that. And it's of course going to be positive or negative, because of course if I start off with something like something squared equals 9, well that something could be positive 3 or negative 3. So it's not just quite as simple as taking the square root. All right, fine. So now I've got this. Then have a look. If I'm going to square root a fraction, it's as simple as taking the square root of the numerator and square root of the denominator. So in other words, I end up with positive or negative root of the numerator. And then the denominator, okay, square root of 4a squared, well square root of 4 is 2, square root of a squared is just a. So it's going to be 2a on the denominator. So I'm square rooting the numerator and the denominator separately. All right, and I guess now, because I want the x on its own, right, I'm pretty much there. Because I want the x on its own, I'm just simply going to take away the 2a from both sides. Okay, so b over 2a from both sides. So in other words, I'll end up with x equals, if I take away b over 2a from both sides, I end up with this, plus or minus square root of b squared minus 4ac, all divided by 2a. And again, you notice that I can make this look a little bit neater, because you've got two fractions, they're each over 2a, so I don't even need to make the denominators the same now. So I can just simply write x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And that there looks very big and complicated, but I can promise you this is incredibly useful. And in fact, it's so useful, it's a formula which we can use when we're dealing with quadratics, hence we call it the quadratic formula. So how on earth do we actually go about using this? So this is basically just completing the square. So all we've done here, and we've just done it on a general form of a quadratic, okay? So how on earth do I actually go about using this? Well, let's suppose I give you something like y equals, let's suppose I give you something like y equals 3x squared plus 5x minus 2. And I ask you to use the quadratic formula on this. So if I want you to use the quadratic formula, what I'm looking for are the X intercepts, okay? So the X intercepts, remember, we get by setting y to be 0. So really, I'm asking you to find the the X intercepts of 3x squared plus 5x minus 2 equals 0, okay? So find me the X intercepts then. Well, you notice in this case, I've got a formula that I can just use. So let's just first of all notice what A is. So A has got to be equal to 3, B is equal to 5, and C is equal to negative 2. So if I want to find the values of x, I just simply need to stick these into my quadratic formula, okay? And you will use this a lot, so let's actually just write this down. So x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Commit that to memory, okay? Just write it out a million times and you'll get it. So the more practice you do, you'll know this. So now all I need to do is stick this in my quadratic formula. So my b is 5, so therefore if I stick negative b in, it'll have negative 5, plus or minus square root of, well, I have b squared, which is going to be 5 squared, minus 4 times by a, which is 3, times by c, which is negative 2, all divided by 2 times a, which is 2 times 3. Okay, so I've literally just stuck my a, b, and c into this formula here, and that's how I've got this line here. Okay, so now I can go through and actually physically tidy this up. So I have negative 5 plus or minus the square root of, well, 5 squared is 25, and then minus 4 times 3 times by negative 2. So, okay, negative 4 times negative 2 is positive 8, and that's going to make 8 times 3, which is going to be 24. So I'm going to add on 24 here, and I'm going to divide all of this by 2 times 3, or divide it by 6. let's have a look at tidying this up slightly further. This is going to be negative 5 plus or minus, well, okay, square root of 25 times plus 24 is going to be square root of 49, all divided by 6. So let's have a look. Well, okay, negative 5 plus or minus square root of 49 is 7, divided by 6. Let's tidy this up. So in other words, I'm going to end up with x equals negative 5 plus 7 over 6, or x equals negative 5 minus 7 over 6. So that's how I deal with the plus or minus. I do one with a plus and one with a minus. Okay, so let's figure out what this is. So I get x equals, well, negative 5 plus 7, that's going to be 2. Divide that by 6, that is going to be 1/3. Okay, so x equals 1/3. The other value of x, well, negative 5 take away 7, that is going to be negative 12. Divide that by 6, that's going to be negative 2. So that's my other value of x as well. So you notice in that case, I haven't had to use any factorizing, haven't had to solve anything at all. Okay, I found my x intercepts just simply by using this newfound formula, and I found x equals 1/3 or x equals negative 2.